In the previous chapter, we looked at the basics of probability. Now we're going to look at probability distributions. And so first off, we need some definitions. A random variable is a variable that has a single numerical value determined by chance for each outcome. The random variable can be discrete, which means you can count them, or it can be continuous, which means there are infinitely many values, but they're associated with a continuous scale of measurement. So it's sort of measuring versus counting. A probability distribution is a probability for each value of a random variable, and there are a couple of things that need to be true for it to be a probability distribution. First off, if you add up all the probabilities, you will get 1, where x assumes all possible values. In other words, your probabilities have to be between 0 and 1 for all the possible outcomes. And then when you add up all possible outcomes, you get to 1 because, of course, something must happen, whether that's it did or did not happen. You have to have some outcome, and therefore you have to add up to 1. So a probability distribution, all the probabilities are between 0 and 1, and all of the probabilities for the event under consideration would add up to 1. Now, if you have a very, very small value of x, such as the one listed there, all those zeros, and then the 1, 2, 3, sometimes you will see that represented in a table as 0 plus, which indicates that it's very, very small. It does not mean it's 0, it just means it's insignificant, and it would not add to our probabilities. Okay, so again, if you say a probability is 0, then you are saying it's impossible. But just because you have something that's 0.0000 and a whole bunch of more zeros, that's not impossible, it's just very, very unlikely. And generally, we use the 5% rule to talk about unusual events. So anything that occurs or has a probability of occurring less than 5% of the time would be unusual. Now, a probability histogram is similar to a relative frequency histogram. If you remember, a relative frequency histogram was one in which we turned all of the frequency values into percentages of the total number of frequency that we got when we added up all the different pieces, all the different classes. But in this case, the vertical scale shows the probabilities instead of the relative percentages. But it looks very similar to a relative frequency histogram. The area of the rectangles or the bars are the same as the probabilities. Now, to find the mean or the standard deviation for probability distribution, basically for the mean, it is the sum of x, and x is the outcome, and then times its probability. And we'll go over an example of this, but basically it's x times its probability, and then you sum all the varieties of x that may occur. The standard deviation, very similar to what we had before, but here it's x minus mu, so that is the particular value. Subtract the mean squared times, again, the probability, though very often what we end up using in our calculations is this one instead, in which you do x squared times the px, so it's very similar to this part, except it's x squared, and then you subtract the mean squared, square root the whole thing, and you have the standard deviation. Don't forget, it's the variance if you just don't have the square root part. So remember that the variance is sigma squared, and notice in both these cases I am using mu and sigma. I'm not using x bar and s, because when it's a probability distribution, it is assumed to be for the entire population. Okay, we round these values, usually use one more decimal place than the number of decimal places used in the random variable x. So for example, if x is all whole numbers, maybe we would round the mean and the standard deviation to the 10th place. Okay, and then finally we have what's called the expected value. the expected value, or E, and you have to be careful because E does not always mean expected value, but for this chapter it does, and that is the mean. So E is the mean, mu up there. The mean of a discrete random variable is the theoretical mean outcome of infinitely many trials, and the average value we would expect, E for expect to get if the trials could continue indefinitely. So note these are the same. So E and mu are the same thing. So that is all of basically the new information, and now let's see some examples. One of the important things is to identify whether or not your random variable is discrete or continuous, and basically it comes down to, is it a measurement or can you count it? Now you might think in your sense, well, I'm measuring, counting, in that kind of the same thing? Not exactly. So let's look. Okay, the total amount in ounces of soft drinks that you consumed in the past year, we would consider this a measurement and therefore continuous, because when you say the amount, really the question becomes, how picky are you about the amount? Are you rounding it to the nearest ounce? Tenth of an ounce, thousandth of an ounce? In other words, you could pick just how many decimal places you want in your measurement, and that's why it becomes a continuous amount. You're not really counting the number of ounces, because you could have partial ounces. On the other hand, if you were to say the number of cans, that would be a discrete thing because you can count the number of cans. Even if you wanted to make allowances for maybe the last can is a partial can, you could still count the number of cans, and so it's discrete. All right, the number of movies that are currently playing in the U.S. Well, movies, you can count them, so that would be a discrete thing. The running time of a randomly selected movie. Now, they always print those generally when you buy a DVD or something, but the thing is, that's still an approximation, usually rounded to the nearest minute. You could go to the second, you could go to the microsecond, and so that makes it a measurement and a continuous random variable. Or how about the cost of making that randomly selected movie? Well, again, you might think that, hey, cost, dollars and cents, but again, when it comes to the current age we live in, which is electronic and over the internet, costs can be a lot finer than just the penny. They can actually go to fractions of a cent. There was a movie a few years back called Office Space, in which the gentleman actually had a scheme to steal the fractions of a penny from a bank. And they thought, who would notice? It's fractions of a penny. Well, it turned out that the bank did so many transactions a day that those fractions of a penny actually added up to millions and millions of dollars, because there were that many transactions. And so even tiny amounts can add up if there are enough of them. So, just again, trying to get a handle on, is it discrete or is it continuous? Now, let's look at an actual probability distribution. We have here, given 5 babies are randomly selected in each group, the random variable is the x. So here's the random variable, and you can see 0, 1, 2, 3, 4, 5. In general, for the discrete random variables, it'll start at 0, that's the none case, and then it'll go up to whatever is the amount in the selection. In this case, it was groups of 5 babies, and so we have 0 for no babies up through all 5 babies. And then what you see over here is the probability that within any group, this is the number of babies with green eyes. Okay, so first we want to determine if this is a probability distribution, and then afterward we want to find the mean and the standard deviation. So first off, if it is a probability distribution, all the values have to be between 0 and 1. And if we look, we can see that they're all less than 1 or greater than 0, and therefore that part works. And then we have to add them all up. And if they come out equal to 1, then we have, between those two things, we can say this is a probability distribution. Now, it is possible that if you look at the numbers in a particular distribution and you add them all up, maybe you come out to 0.999, or maybe you come out to 1.001 or something like that. And so what you want to check is that just a rounding error? Because I'm only listing 3 digits here. If I were to list the 4th digit and then add them all up, I might have actually come out more than 1. So it just depends on your rounding sometimes. But if you're pretty close to 1, we're going to say that is a valid consideration. All right, so now to do the mean. Again, the mean is the sum of the x values times their probability values. So here's 0 times the 0.528, and then 1 times the 0.36, 2 times the 0.098, 3 times the 0.013, and so forth. Add them all up, and we end up with 0.599. You could use that as your mean, or you could round it to 0.6. Since each of these were to the 1's place, I rounded that to the 10th place. But you know, honestly, going with that with your calculator, 0.599 would have been just fine. Now, to do the standard deviation, I have to do something that's very similar to what I did up there, except it's squared. So it looks very similar to begin with, and then notice instead of 2 it's 4, instead of 3 it's 9, instead of 4 it's 16. And so I do all of that, then add them up. I get 0.855, and now I have my equation. Notice the equation has this part here that I just calculated, subtracting the mu squared. And so 0.855 subtract the 0.599 squared, and that gives me my answer, 0.704. If I wanted to round it to the 10th place, it would be 0.7. The thing to note here is if you round this thing overly, like let's say you rounded it to 1, because 0.6 would round up to 1 if you wanted the 1's place, you would get a different answer after plugging it in to find out your standard deviation. So I would just go ahead and carry a few extra decimal places before you start rounding, just to make sure that your answer comes out appropriately. So there's an example of a probability distribution and finding its mean and standard deviation. Alright, now using that same probability distribution, we want to look at what is the probability of having exactly 3 babies with green eyes? What is the probability of having 3 or more babies with green eyes? Which probability is the most relevant for determining whether or not 3 babies with green eyes is unusually high? And then, is 3 an unusually high number? So we're going to use this table to answer these questions. First off, exactly 3. Well, we just go to where it's 3, we read it right off the table. So having 3 babies out of the 5 with green eyes had a chance of 0.013, which is about 1.3%. 3 or more means adding the 3, the 4, and the 5. Now the 0 plus I can ignore because it's insignificant, but basically the 0.013 and the 0.01 gives me a chance of 0.014. Now the question is, should I use this or use that in determining whether or not 3 is the most relevant? The answer is we're going to pick the 3 or more because the additional amount is not significantly different than this one, and so we're going to use 3 or more. So really, 3, 4, or 5, that answer would be the most relevant to answering our final question, which is 3 an unusually high number of babies with green eyes? So, in other words, this question is about if we randomly selected 5 babies, would it be unusual that 3 or more of them would have green eyes? And the answer is yes, it would be unusual because 0.014, which is what we got when we added up the 3 and the 4, 0.014, that's less than the 5%. That's 1%, that's 5%. So 3 would be unusually high number of babies born with green eyes. So here we had, can we tell if it's a probability distribution? Can we find its mean and standard deviation? And then in this part we actually read the table to find out information. Alright, now, in the next problem, we said, and this will be a different one, it says, let the random variable x represent the number of girls in a family of 4 children. Construct a table describing the probability distribution, then find the mean, standard deviation, and the variance. So here, we want to construct the probability distribution table, and we need to do that first by looking at the sample space. And so let's take a look at what we have here. This would be the sample space of 4 children. So the B's for boys, the G's for girls, all boys. This would be 1 girl, and then in other cases 2 girls, and then in other cases 3 girls. There are 16 possibilities. If you think about it this way, the chances of a boy or girl are, you have 2 outcomes, 4 of them, so 2 times 2 times 2 times 2, that's 16 possible outcomes. Now, then we want to build our table, and here's where we're building our table over here. So the key is the x is, in this case, we want number of girls. That's all B's, so that's no girls. So there is 1 case out of the 16 that had no girls. Okay, then you have to do how many cases had 1 girl. That has 1 girl, that has 1 girl, that has 1 girl, and that has 1 girl. I am using an order matters for the different outcomes. In other words, this one was the 4th child was a girl. This one was the 3rd child was the girl. The 2nd child was the girl, and then here was the 1st child was the girl. So that's a different place. That's a different potential outcome. There are 4 of them that had 1 girl. So 1, that's the outcome. There were 4 out of the 16. That's its probability. There were 6 out of the 16 that had 2 and 2. 4 out of the 16 in which there were 3 girls. It has to match the 3 boys case. And then there was only 1 case in which we had all girls. And so now I have a probability distribution. It doesn't matter that these are all fractions instead of decimals. And so I can go ahead, like I did up above, and find my mean and my standard deviation. And of course the variance is just the standard deviation squared. So, first off, each one of these multiplied together and then all of them added up. So I just left it in fraction form. It turns out you get 32 over 16, which is 2. So the mean of this is 2. And actually, if you kind of think about it, you have 4 children. You have an equally likely chance of having a boy or a girl. So on average, you would have 2 boys and 2 girls on average. Okay, now we're going to do the formula for the standard deviation. So notice instead of the x, we use x squared here. So 0, 1, 4, 9, 16. This actually adds up to 80. Got a little typo here. This actually adds up to 80 over 16, which is 5. Now I can plug them into my formula. And so I'm going to have 5, subtract 2 squared, which is 4. 5 minus 4 is 1. The square root of 1 is 1. So standard deviation is 1, and the variance would be 1. And so there you have an example of creating the probability distribution and then determining the mean and standard deviation and variance. So that's it for section 1 of chapter 4.